Okay, so last time we did the nth term test and the integral test, right? So I wanted to start with an example that's maybe a little bit out of the ordinary. So let's look at this together. Okay. So let's go over here to the whiteboard and we'll deal with this. So how about this? And I would encourage you to kind of work on this with someone nearby you. So here's a series. What about this? So what about sum of, let's say, n going from 2 to infinity, logarithm of n over n, just over n, okay? So what do you think is going on with this series, okay? So let's just take a couple of minutes with those around you in light of, what we learned last time. So first of all, let me just point out, in the hierarchy of things that we know so far, is this a geometric series? No. Is it a telescoping series? No. Okay. Do the terms go to 0? Do the terms go to 0? Like if I look at the individual summands, they're of the form log n over n. As n goes to infinity, does log n over n go to 0? Yes. So what can I conclude from that? Nothing. Okay. If the terms didn't go to 0, then I would know the series diverged. But I can't conclude anything from the fact that the terms do go to 0. So now I have to resort to other things. Well, I only know one other thing at this point, and that's the integral test. You know what I mean? We had the P series that we were able to sort everything out about, but now we have the integral test at our disposal as well. So clearly what I'm asking you to do here is to please try to apply the integral test to this thing. Does that make sense? Okay, and what does that mean you're going to need to check about this? These terms, log n over n, thought of as a function, log x over x. What would you need to check about that function? It needs to be positive and decreasing, yes? Eventually positive and decreasing, okay? So work on this for a few minutes and then we'll regroup and kind of talk it through. All right, what do you guys have for me? What do you think? Does this series converge or diverge, and why? Yeah.
So I have a different way that I think it converges. So
Mm-hmm.
wrong.
It diverges, yes.
Okay. So I know you can do the integral test. The way I look at it, I thought of it as more of a P-series way.
Okay.
So if you separate this out into natural log, so say you have 1 over n, right? We know that diverges, right? And
series 1 over n diverges, yes. So
we have natural log of n over n. And so natural log of 3 is greater than 1. Natural log of 4 is greater than 1. And so
in fact, natural log of n goes to infinity. So what you basically are saying is that, look, logarithm of n, that's like always bigger than or equal to like 1, right? So like logarithm of n over n is bigger than or equal to 1 over n, yes? So therefore, the series logarithm of n over n is like bigger than or equal to the series what? 1 over n. What you're doing right here is you're applying something called the comparison test, which is something that we're going to talk about today, actually. This is the comparison test. And of course, this side over here, what's this equal to? Plus infinity, for crying out loud, right? So therefore, what's this guy going to be? Plus infinity also, right? So you compared it to a P-series and got it, yeah? Okay, so yeah, that is one way to sort of slay this problem, and it segues nicely into what we'll talk about today. But what's another way to do this? So that's we could do this with the comparison test. What's another way to do this? Which I suggested. What should we put f of x equal to in the integral test? Like logarithm of x over x, yeah? Okay. First of all, is this thing positive and decreasing? Like, how could I tell if it's decreasing or not? What would I do? Take the derivative, right? So f prime of x, okay, this is, you know, maybe we're a little rusty with some of this, but let's knock the rust off here. It's going to be low, which is x, times the derivative of the high, which is 1 over x, minus high, which is logarithm of x, times the derivative of the low, which is 1. All over the denominator squared. Okay, so that means the derivative is 1 minus logarithm of x over x squared. Okay. And that actually, I mean, the bottom is always positive, right? I mean, that's x squared after all. In the top, if you think about it, we're thinking about like what the sign of the numerator is for various values of x. If x is like past e, like what's logarithm of e, by the way? Natural logarithm of e? 1. But if I plug in things beyond e, right, then the logarithm of that's going to be bigger than 1. And so 1 minus something bigger than 1 is always less than 0. And this is for x bigger than e, right? So that means that this function is decreasing. It's also positive. If you think about it, I mean, if I plug in things, you know, beyond e, of course, I'm going to always have something positive here. And it's continuous for x bigger than e, right? So it has all those properties. So that means that like this series right here is going to have the same behavior. This series right here is going to have the same behavior as the integral from, let's just say 2 to infinity. I could have gone from e to infinity, but you know, who cares, right? I mean, we're just talking about kind of the front end of this. It's not that big of a deal. It's the same behavior as the integral from 2 to infinity of logarithm of x over x dx. And how do I deal with that integral? So, and by the way, this, what I'm applying here is the integral test, yeah? This is like the integral test. Integral test. Okay? So what do I do with this guy? The integral from 2 to infinity of logarithm of x over x dx. What could I do with that? Help me out here. I don't think that's necessary. Yeah, we would do that, but I'm just asking you, can you think of an like how would I find the you're exactly right, but how would I find the antiderivative of logarithm of x over x? That's kind of my chief concern right now. U substitution, what am I going to put u equal to? Yeah, if I put u equal to logarithm of x, then du is literally just 1 over x dx. And this thing works out beautifully. Okay? So, so like u is equal to logarithm of x, du is 1 over x dx. Amazing, look at this. This is going to be the integral. What is it? It's going to be u du, isn't it? And what are my new limits of integration? So if x, right, remember, so this, right, these limits were from x equal to 2 to x equal to infinity. So what are my new limits in u? If x is 2, what is u? If x is 2, then what is u? It's logarithm of 2, yeah? What if x is like going to infinity? What does u go to? Think about it. If x goes to infinity, right? I should be not as sloppy with this. What I mean by x equal infinity is I mean x goes to infinity. If x goes to infinity, what does u go to? What does logarithm of x go to as x goes to infinity? Infinity. Right? Infinity. Excuse me, I'm integrating the function like y equal to u from the logarithm of 2 to infinity. What does that look like? That's just a, that's just a straight line. Does that make sense? Clearly that's going to have infinite area, correct? I mean, think about it. Here I'm just integrating, if here's logarithm of 2 right here, right? Here's logarithm of 2 right here. And I'm just integrating this, right? The line y equal to u, basically, from logarithm of 2 to infinity. Clearly, that has a lot of area underneath it, right? Okay. So what does this thing integrate to? Plus infinity, yeah? Because this integral, because this thing integrates to infinity, the series also sums to infinity. So the conclusion is that this series diverges. Diverges. Okay, so we had a couple of approaches for that one. All right? Now, let me ask you a follow-up question to this. Okay, so any questions on this? Please ask questions. Okay, either of these approaches is valid. We didn't technically know the comparison test yet, but that's coming up here pretty soon. Okay? But any questions on that? Okay, let's move on. What about this? What if I asked you to compute the sum? Let's do n going from 2 to infinity, logarithm of n over n squared. What about that? Logarithm of n over n squared. What do you guys think about that? Okay, I'm going to give you a couple of minutes to kind of think about that on your own or with someone next to you. But think about this one. Okay, what would you do? All right. So what are we going to apply again, just to make sure we were hearing one another? Yeah, the integral test. And what do we compare this thing to? What is it I'm going to be looking at instead? So technically speaking, I should do the same thing I did before, where I form the function, I take the derivative. I need to make sure that the derivative was negative eventually. Yeah, it will be, okay? Derivative will be negative eventually. This the function is positive for values of x. So what integral am I going to compare this to? The integral from where to where? Of logarithm of x over x squared dx. What do we do with this mess? What are we going to do with that? What do you guys think? Oh, okay. Ooh. Okay, so if you integrate this thing by parts, okay, so hang on, let me sort of rewrite this. The integral from 2 to infinity, x to the minus 2 times logarithm of x dx. Okay, so so somebody suggested integration by parts. What's u going to be? And what is dv going to be? Okay, so what's going to get priority is being put equal to u in this case. Natural logarithm of x. Who wants to find the antiderivative of that garbage, right? Okay, and then dv is going to be x to the minus 2 dx. Okay? And then du, what's du? Du is is what? 1 over x dx. And what is v? So think about it. V means I need to find the antiderivative of x to the minus 2. What is the antiderivative of x to the minus 2? Say, what's that, Jared? No, the antiderivative, I'm going to have to add 1 to the power, right? Negative x to the negative 1, right? So negative 1 over x. Okay, so let's see here. So this is going to be, okay, you go u times v, which is negative logarithm of x over x, and I'm evaluating this between 2 and infinity, yeah? Which is weird, but okay. We can deal with it. Minus the integral of v du. But we have a negative 1 over x, right? V is negative 1 over x. Okay, so it's going to be plus the integral from 2 to infinity of 1 over x squared dx. Okay, so what in the world do I mean by, what do I mean by this, you know, putting infinity up here and asking to plug in? What am I talking about when I write integrated between 2 and infinity? What do I mean by that? What do I mean by plugging in infinity? What am I talking about? I mean to let x go to infinity, yes? So what happens if I let x go to infinity in negative logarithm of x over x? What happens if I let x go to infinity in that? What would I get? Right, but what wins? The x does. So what's that limit going to be? Right, so it will be infinity over infinity, but we know that the logarithm is destroyed by the polynomial, yes? Therefore, that limit will be 0. So it will be 0 minus negative, which is plus logarithm of 2 over 2. And then I have this other integral, plus the integral from 2 to infinity of 1 over x squared dx. Now let me ask you something. What about this integral right here? Does this integral converge? Do we have to really go any further? Look, it's the integral from 2 to infinity of 1 over x squared. We've done this sort of thing before. What do we know about this? It will converge, yes? Just like the sum in going from 2 to infinity of 1 over n squared converges, right? That's something we should know at this, or that we do know at this point. This thing converges, right? We don't really need to go any further. And of course, log 2 over 2, that's just a number. Therefore, this integral right here converges. Right? We didn't sort out what that number was specifically, but it doesn't really matter. And therefore, since this integral converges, what do we say about this guy right here? That converges. Okay, let me ask you a question. Okay. What do you think is going to be true about this integral? Integral n going from 2 to infinity, logarithm of n over n to the p. Okay? These are often referred to as logarithmic. What do you think they're called? I just put into the p in the bottom. It's going to be a logarithmic p series. What do you think is going to be true about these guys? Anybody care to make a guess? Right, it actually behaves exactly the same as the p-series. Turns out putting a logarithm in the numerator doesn't do jack squat. It's sort of interesting, yeah? Okay, so this thing will diverges if p is less than or equal to 1. And what does it do if p is greater than 1? Right, it converges if p is greater than 1. We just realized that, you know, if p is, so in this case, p was 2. In the last example, p was 1, and we got divergence. Yes, and it turns out that we could sort of use similar reasoning to show that actually these logarithmic p-series have the exact same behavior as the p-series situation. Okay, logarithmic p-series behave exactly like the p-series situation. You just basically replace the 1 with logarithm of n, and the behavior is exactly the same. Okay, so that's something that you can just use at will. If you happen to run across a series, I want you to have lots of intuition about what series are tending to behave like before you even start to apply tests. If you see like something like 1 over n to a power, you immediately know that's a p-series with p bigger than 1, therefore the thing converges. The same sort of rationale will apply if you happen to have a logarithm in the numerator. Does that make sense? Okay, so you have p-series, you have logarithmic p-series. Just want to make sure that we're on the same page there. Any questions on that? Yeah, Daniel.
So, you were just like applying that growth hierarchy of like, so logarithm is slower than polynomial.
Right, we applied the fact that the logarithm grows slower than the polynomial right there. Yeah.
So then, are there other series similar to p-series where like, let's say, like if the numerator is lower on the growth hierarchy and the denominator is greater on the hierarchy, that if p is not necessarily p, but if the denominator is greater than a number, then it converges. And then if the denominator is lower than a number, then it backwards or something like that.
I mean, this is one of the main ones. And by the way, I'll even let you look. Okay. Suppose that instead of just logarithm of n up here, I had logarithm of n raised to the q power. Do you think that's going to change anything? No, it doesn't matter. I mean, q could be 37 trillion. Okay, that's supposed to be a q, not an 8. Okay, I just want to make sure that's clear. Okay, so q. Okay, so that's to the power q upstairs. Okay, so you could have any power of logarithm upstairs. And the only thing that really matters is the power on n downstairs. Okay. And Daniel, I mean, you're right that what's going on here is kind of this growth hierarchy. That's what's controlling what's happening. You can really get off into the weeds with some of this stuff, but I just want to make sure that we're clear about logarithmic p-series and p-series, what's happening with the power on n in the denominator. That's what's controlling what converges and what diverges. Okay. Any other questions on that? Okay. So what I want to do now is go into the presentation here. Yeah. So comparisons of series. Okay, so let's talk about comparisons of series. Okay, so Michael already gave a little mini lecture to us about this as it pertained to the, comparing the series logarithm of n over n to the harmonic series. Okay, and that's a great example. So there are 2 types of comparison tests. There's something called the direct comparison test, and limit comparison test. What Michael just did is called the direct comparison test. Okay, so what did he do? He basically said, hey, I want to know what's going on with this series, logarithm of n over n. And what did you do, Michael? Yeah, oops, logarithm of n, yes. This is greater than or equal to the sum n going from 1 to infinity, because you could just compare it term by term, yes? Greater than or equal to sum n going from 2 to infinity of 1 over n, because logarithm of n is bigger than or equal to 1 over, logarithm of n over n is bigger than or equal to 1 over n, yes? And since this guy is known to diverge, since this guy is known to diverge, this thing diverges, then what does that tell you about the other series as well? Since it's above the other one, that series will also diverge. In fact, it's important that this thing diverges to plus infinity. Okay, so that means that this guy over here also diverges to plus infinity. That, my friends, is called the direct comparison test. You directly compare it to a known series. Does that make sense? You directly compare it to a known series. Okay? All right, here's another example. What about this? Okay, so this is another example of direct comparison. What about this series? Suppose I did sum n going from 2 to infinity, 1 over 2n plus 3. What do you think about that? What do you think about that? Or actually, let me fix this. 2n squared plus 3. 2n squared plus 3, okay? Make a little bit easier of an example. Okay, just think about this for a minute. What in your mind do you think this is basically behaving like? Basically 1 over n squared. You think the 2, okay, well, that might not be changing things all that much. The plus 3, that probably isn't changing things all that much, yes? Okay? And what you can say here is, look, notice that 1 over 2n squared plus 3, okay? Isn't it true that this is like less than or equal to 1 over 2n squared? You know what I'm saying? I mean, adding 3 in the denominator is going to make things smaller. Does that make sense? Okay. And so this series is smaller than or equal to sum n going from 2 to infinity, 1 over 2n squared. And what can I do with the 1 over 2? What can I do with that? You can just pull that thing out. It's a constant. So this is 1 over n squared. And what do we know about this guy over here on the right? What does this guy do? This guy converges. Therefore, what can we conclude about the other thing? Since I'm just adding positive terms every time, okay? Since I'm just adding positive terms every time with each one of these series, the guy on the left-hand side also has to converge, yes? The guy on the right-hand side adds up to something finite. The guy on the left-hand side also must add up to something finite. Right? That's how direct comparison works in this particular case. It's very important that I'm dealing with sums that have positive terms in them. Okay. All right. So I want to do another example here. So what about this? Well, actually, I'll go to the next slide here just so I can get a little bit more room. Any questions on that? You guys understand what we did? Now, in the one case, the one that Michael brought up, in the one case, I slipped a diverging series below the series in question, yes? I slipped a diverging series below the series in question. But in this case, I slipped a converging series above the series in question to make a conclusion, yes? Now, what is not helpful, my friends, is to slip a converging series below the series in question. Because that's not going to tell you anything, yeah? If I slip a converging series below the series in question, I say, well, that thing converges. Well, that can't tell you anything about the bigger series. Does that make sense? That bigger series could still add up to infinity. You guys know what I mean? Okay? So would that be like me saying something like this? I say, well, look, 1 over n is clearly bigger than or equal to 1 over n squared. Yes? Isn't that true? And so therefore, sum n going from 1 to infinity, 1 over n, is greater than or equal to sum n going from 1 to infinity, 1 over n squared. This guy converges. This guy converges. But what does that tell me about the other series? Nothing, yeah? I mean, I have this series that converges that's smaller than the series in question, yeah? And so I would be like, well, I don't know. I don't know what's going on with this. So if you are trying to say something about your series, you need to either slip a diverging series below it or a converging series above it. Do you hear what I'm saying here? You slip a diverging series below it or a converging series above it to make your conclusion. So you have to be careful about how you apply the so-called direct comparison test. Okay? So let's see what the direct comparison test says. 3 warm-up problems. We actually already did them. But here's what the direct comparison test says. Okay, we're only dealing with series of positive terms here. We're still just dealing with series of positive terms. If 0 is less than an is less than or equal to bn for all n, well, if series bn converges, then what can we conclude about series an? It also converges, yes? Series bn, after all, is, I mean, think about it. The way this is set up, series an, because each term is, each an is less than or equal to the other guys, then the series an is below series bn. If series bn converges, what does that imply about series an? Right, if this thing converges, that implies that this guy converges. Yes? Okay, on the other hand, what if series an diverges? What could I say then? If this guy diverges, what does that say about the series that's above it? Yeah, this thing diverges also, right? Diverges technically to plus infinity. That's actually important in this particular case. It's very important that we be dealing with series of positive terms here. Otherwise, we can get into some monkey business here. Okay, so if the upper series converges, so does the lower series. If the lower series diverges, so does the upper series. That's how direct comparison works. Does that make sense? Hopefully. Hopefully that makes sense. Okay. Let's see here. What about this example? I have this example kind of written down here. What if it was this? Sum of what? N going from 1 to infinity, 1 over the square root of n cubed plus 1. What would you do with that? What do you think about that? No, it wouldn't be wrong because look, adding 1 inside of the square root actually decreases these terms. That makes sense? So this thing is less than or equal to sum n going from 1 to infinity, 1 over the square root of what? N cubed, which by the way is just the same as the sum n going from 1 to infinity, 1 over n to the 3/2, just like you were saying, Jared, right? Oops. N to the 3/2. And what do we say about this series? This thing converges. Okay, how? How does it converge? How do you know? It's a P series, right? So P is equal to 3/2. P is equal to 3/2, which is greater than 1, right? Therefore, since this thing converges, so does this original thing over here that's actually smaller than it. Does that make sense? So direct comparison is a pretty useful tool. Please ask questions. Any questions on that? All right. So one test that I think kind of gets short shrift in calculus classes typically is something called the limit comparison test, but I don't want to give it short shrift. I want to make sure that you guys really understand this. This actually is probably one of the most powerful tests that has ever been concocted by mankind for series, right? So for convergence tests for series, okay? I'll come back and use that in just a minute. But the limit comparison test says if, once again, we're assuming that we are dealing with positive terms only. All the terms have to be positive. And if the limit of the ratio of the terms is basically some constant, okay? If the limit of the ratio of the terms is some constant, then basically, and by the way, L has to be finite and positive, right? So L is the limit of these things. L has to be finite and positive. Then it turns out that both of those series will have the same behavior. Does that make sense? The series will have the exact same behavior. And actually, here's the big secret. Limit comparison actually subsumes direct comparison. Like limit comparison is really all you need. Direct comparison is convenient and you can apply it very quickly. It turns out limit comparison is way more powerful than direct comparison. Anytime you could use direct comparison, you could have also used limit comparison. Okay? So for instance, does this make sense? So basically, this allows you to be able to look at the terms and say, you know what, that basically is behaving like 1 over n squared, like series 1 over n squared. It allows you to make that rigorous, okay? So any questions on this? Because we're going to look at some examples here. Okay, what about this? Let me go back one slide. Let's look at this one. What about series n going from 1 to infinity of 5n minus 3 over n squared minus 2n plus 5. What do you guys think about that? What do you guys think about that? Look at that disaster. What do you think really matters? Okay, in the numerator, what's controlling things is probably the 5n. Does that make sense? And what's controlling things downstairs is basically what? N squared. So what do you think this is basically behaving like? Basically n over n squared. The 5, who even cares about the 5? Do you know what I'm saying? So basically you think that these terms are behaving somewhat like 1 over n. Does that make sense? Okay. So let's do limit comparison with series n going from 1 to infinity, 1 over n. Okay? So note the following. What happens if I take 5n minus 3 over n squared minus 2n plus 5, and I divide that thing by 1 over n? Right? They said to take an over bn and compute the limit, yes? Take the limit of an over bn. So right now what I'm doing is I'm thinking of this as being my an. Yes, this is an. And I'm thinking of this guy right here as being bn. Okay? So I'm basically taking the ratio of an over bn. And if the n flips upstairs, what do we get? Isn't it going to be like 5n squared minus 3n? Because the n would multiply by that numerator. And downstairs, I would get n squared minus 2n plus 5, right? What does that limit to as n goes to infinity? 5, which is finite and positive, yes? That's what limit comparison said, right? This is a finite positive limit. Finite positive limit, right? So sometimes I like to do limit, I like to call limit comparison test, I just go LCT for limit comparison test. So by LCT, our series behaves like what? What does it behave like? A limit comparison test, it behaves like series 1 over n. Series n going from 1 to infinity, 1 over n. And therefore does what? What do we know about series 1 over n? Diverges, and therefore diverges to plus infinity. Okay? Let me just say, let me just to be clear, 2 plus infinities is what we mean here. So 2 plus infinity. Okay? Okay? Does that make sense? Limit comparison test subsumes direct comparison, but sometimes it's just convenient to use direct comparison really quickly. Limit comparison, you have to compute this blasted limit. Does that make sense? You have to actually take the ratio of the terms from the series you started with and the series you're comparing it to. You have to take that limit, and that can be a little annoying. Okay. All right. So do you guys see why limit comparison would be really, really helpful? Because what does it allow you to do? Well, just throw out a bunch of junk. Does that make sense? You basically can say, well, none of that junk even matters. Yeah. What really matters is this stuff. And now all of a sudden I see that this thing is behaving like a P series. Yeah. What if this power right here, let me just ask you a question. What if this power right here would have been to the power 3 instead of 2? What if that would have been to the power 3 instead of 2? How would that have changed things? What's that? That's right. We would have been comparing it to 1 over n squared instead. Yes? And therefore, what would we have concluded about this series? By the way, everything else would have worked out exactly the same, except this would have been a squared. This would have been, right? This would have been a cube. This would have been a cube, and this would have been a squared right here. And we still would have gone to 5. Do you see what I'm saying? Yeah? And instead of, right, this would have been a squared. Instead of diverging, what would we have said? Converges. Because after all, the series 1 over n squared is a P series with P equal to 2. Yeah? Yeah. Well, no, that's not a hasty assumption. That is something that you can absolutely conclude, and it follows from the limit comparison test, yes? Because you would take the ratio of that with 1 over n. That 1 over n would flip up and raise all the powers of the numerator up by 1. Does that make sense? And that thing would limit to a positive number, and so you can make a conclusion about it. And by the way, here's a little secret that I'm going to tell you and that you can use later on when we get there. Limit comparison test you don't have to have all positive terms. It actually works all the time. Does that make sense? So you just have to find something to compare it to, compute the limit, and this is just a really slick test that really makes a lot of problems collapse pretty easily. Okay? Other questions? That is limit comparison, right? So there's the limit comparison test right there. I wanna delete this and we can look at that one more time again. It says that these things have to be positive, but the dirty little secret here is later on, I'm going to let you just use it all the time. Does that make sense? Like you don't necessarily have to assume that the terms are all positive. That's actually not necessary, okay? Turns out it works all the time. For direct comparison, it is very important that everything in sight be positive, okay? But for limit comparison, that is not a critical assumption at all, okay? But what we do is we find a series that is easier to work with, that we understand, and that has the property that when you take the ratio of the terms and get like some positive limit, then those two series will behave the same. They either both converge or both diverge. Okay? Any questions on that? Questions? All right. What do we have so far? Right? Look, series converges precisely if the limit of the sequence of partial sums converges. Yes? We know how to deal with geometric series. We know how to deal with telescoping series. What else do we know? P series, integral test. Yeah? Logarithmic P series. We know direct comparison. And what else do we know? Huh? Oh yeah, limit comparison test. And one that we forgot was what? Nth term test. Somebody just said it, right? The nth term test was really something we should have mentioned back at the beginning. Right? The nth term test, can I ever conclude convergence from the nth term test? No. Nth term test, you want to make sure the terms go to 0. If they don't go to 0, if the terms don't go to 0, what do we conclude immediately? Series diverges. If the terms do go to 0, convergence is a possibility. And we have to look at other tests to try to sort out what's happening. Okay, so that's just a review of what we know so far. All right, that's all I have for now.